Alrighty, so this will be the final part for this week. I know that we are running out of time, but I think it will be very beneficial for us to really do this exercise together about deriving the running time for the recursive algorithm for the binary search. And we talk about how you can do the linear search that we did in the last part about linear algorithm on the array, how we can derive its recurrence relation and unfold it to solve it. And we wanted to apply the same process for binary search and see what we got, right? Right, so we're going to have the T of n over here to derive the running time function as for the binary search. This will be a very standard process to really apply for any future recursive algorithm that we're going to talk about. For example, merge sort and also quick sort. And then n over here will just be the size of the input array. We'll think about it's going to be the size of the subproblem that we actually want to solve whenever we want to actually make a recursive call. Right, so let's now talk about what that running time function should be. Right, let's now go as we actually analyzed before. Let's talk about different cases. I'm going to just box the different cases over here. Right, we got base case number 1 over here, which is for empty range, and we got base case number 2, which is for the range of in the range of a single element over here. That's base case number 2. And then we got a recursive case. And for the recursive case, either we recur on the left, right, over here, or we recur on the left. Sorry, we recur on the left, which is over here, or we recur on the right, which is number 2 over here, or we simply have found the elements is a hit of the key being searched for. In that case, we're just going to return true, right? So these are the 3 cases in the recursive case, right? So these are the 3. Of course, we choose the one that will take the maximum time, since each one of them is going to happen, but not all of them, right? Cannot be more than 2, more than 1 that actually happen at the same time. So it's either this one or this one or this one. Alrighty, let's now take a look at the running time over here, right? You can see the first one over here, when from is larger than 2, we talk about is the empty range. So that will correspond to the empty input. In that case, what do? We simply return false because we cannot find the elements in the empty range. So that will be just big O of 1. Not 0, but 1, because we still need to do the return over here. So it's simply big O of 1. Right? We simply put the 1 over here. Right? What about the second base case over here? When the range is simply just 1. Right? So that's corresponding to the 1 over here. In that case, what do? We do the return. We do some array indexing. We do some relational comparison, so that will be still big O of 1. So that means we'll still just put a 1 over here, right? What about the recursive case? Basically, we either recur on the left, in which case we are simply just going to go on this particular part. It's going to go from to middle minus 1. In this case, what would be the size for the strictly smaller problem? Well, it's exactly n over 2. Right? Or we can actually go for this particular recursive case. In that case, it would be just this part. Of course, we don't really go to 2 parts at the same time. It's either one, but not both, right? And this one, symmetrically, is also going to be halving the size. So that's also n over 2, right? So what should we do? A very common mistake is to write the following. Let me show it to you, but it's wrong, right? Because I may either go to this or this. So that's why I might say T of n divided by 2 plus T of n divided by 2. And let's say that this is totally wrong. All right. Let me just write it down and also cross it out. This is simply just wrong, right? Because we never actually recur on the left and the right at the same time. If we decide that, for example, the key should really exist in this particular half, we'll simply disregard the other half, right? So there should be only 1, but not both. So what should we write down, right? I'm going to repeat a mistake somewhere to make a note for you. But for now, let's put inside the panda, let's better just put a final answer, right? What should that be? Well, it's going to be basically, let's say, if we decide to go to the left, for example, in that case, it's going to be T of n divided by 2. And then, in that case, we still have the return. So there will be still some work to do. For example, you also have to calculate middle minus 1 and etc. So I'm going to say plus 1 over here, right? Of course, going either this way or this way over here is going to take more work than just constant. So that's why this case over here is going to be dominated by either this recursive call or this recursive call. That's why we actually say this, right? Just make sure you understand how each case is actually analyzed and formulated over here, right? Let me just repeat the mistake I made, right? So what's really wrong is over here. When you say T of n, is actually T of n minus 2 plus T of n minus 2, right? You might be thinking that this might be for the left and this might be for the right, right? But the problem is they cannot actually happen at the same time, right? So this part over here is simply just wrong. Okay, so this is actually no, wrong, because either we actually go to the left or we go to the right, but not both. All right, just enough space to put that remark. Okay, over here. So it's either left or right, but not both. Right? So just remember why this particular answer is wrong. And also when you try to do the unfolding, you will be shocked about how much more expensive it is if you actually got this formulated running time. Right? Just be careful. Right? So this is our final recurrence relation based on the code of the binary search. All right. As you can see, it is very important for you to know how to formulate the recurrence relation before you can unfold it to solve it, right? Let's now try to solve it. All right, so let's now try to work out exactly the detail over here, right? Let's now do this together with you, okay? We got these two base cases. Eventually, we're hoping that unfolding, we want to see how many times of unfolding do we need to really do in order to get to one of the base cases. That'll be the goal. But to do that, we need to observe the pattern of unfolding. Before we can observe the pattern, we need to have examples of unfolding. I would suggest do at least maybe 2 to 3 unfoldings before you can see the pattern. Simply doing just one, usually it's not that enough, right? You should do at least 2 or 3. Let's try to do that. I'm going to start with, over here, T of n, right? So I'm going to say T of n over here, by definition, it is T of n divided by 2 plus 1, right? By definition over here. And I'm going to unfold over here, which means I'm going to substitute n over here by n divided by 2, right? That's what I'm going to do. Right, so this will be equal to, so what I will do is I'm going to put n divided by 2 into a box, right? That means I'm going to substitute n over here by n divided by 2. Substitute over here n divided by 2. So that will be n divided by 2 and then divided by 2, which will be n divided by 4 and then plus 1. Agree? All right, let's now take a look. It will be basically just over here. Let me just put it out. So T of n divided by 4 plus 1 and then plus 1. Let's do some annotation here right away. This part over here is exactly what we actually calculated as the T of n divided by 2. And the plus 1 over here is corresponding to the plus 1 over here, right? This one shouldn't be overlooked, right? Let's see again. It's so critical actually to see exactly how we go from here to here. That's really the critical step you need to do before you can observe. The way we got to here, you can think about this part is exactly equal to this part over here is exactly equal to this part, because let me just do one more highlights, right? You can think about this part over here is exactly equal to this part over here, right? The reason is if you actually substitute n over 2 for n, in that case, substitute every occurrence of n by n over 2. In that case, we'll get n over 2 over 2, which will be n over 4. And then plus 1 over here. All right, that's one unfolding. Let's do one more unfolding, one more. Shall we? Let's say, let me use this color here. Let's say n over 4. All right, let's use this one here, n over 4. So what should we do? So what we should do is we're going to substitute n over here by n over 4. This by n over 4. N over 4 over 2 will be 4 times 2, 8. N over 8 plus 1. Right? Let's now do it. So it's going to be equal to t of n over 8 over here, and then plus 1. And this part over here is really corresponding to this part over here. Let me just try to see if I can find that color over here. Yeah, that should be okay. Right? You can think about this part here. This part over here, t of n over 4, is really corresponding to this part over here. Right? And then you can see the plus 1 over here and plus 1 over here. Don't overlook them. They should be put over here. Plus 1 and also plus 1. And one more annotation over here. You should definitely study the annotation yourself, maybe more carefully, right? As I'm doing the unfolding, I try to be as detailed as possible over here. So this part here is really t of n over 4, right? T of n over 4, replace n by n over 4. So that'll be n over 8, which is exactly what we have over here. And then plus 1, we got plus 1 over here. Apart from that, we got this plus 1, corresponding to this plus 1, and this plus 1 over here. Agree? Okay. If you really like, of course, you can also put the parentheses around if you like. But I'm just going to omit that because plus 1 is easier for it to calculate exactly how many plus 1 we should have at the end. Right? I think so far we have done 2 unfoldings. I think that should be enough, right? Let's now try to see what the pattern is. You know what? Let me do one more. Why don't I do one more, just for completeness? I don't mind doing one more. This one here, let's say we want to actually do, what about I do purple over here? What about this guy over here? N over 8, right? Without looking at the formula, I already know what the pattern is. It's going to be t over n, t of n over 16 over here, and then plus 1. And then plus 1, plus 1, plus 1. Plus 1, plus 1, plus 1. Alright? And the purple, do I have purple highlights? I think I should have. Okay, how about here? Right? You can think about this part over here, t of n over 8, is really unfolded into t of n over 16 and plus 1 over here, right? Over here, let me just highlight a little bit better. Right? And you can see the plus 1, plus 1, plus 1, plus 1, plus 1, plus 1. Right? You will definitely see the unfolding as well on the slides. But I think it's really important for me to try to derive step by step together with you. All right? And of course, this part over here really is this part over here. Oh, sorry, purple. So this part over here really is what we're aiming to actually calculate. So this one here is t of n over 8. Right? I think we have done 3 unfolding. That's enough, right? What I really want to do, and I'll left that as an exercise for you to pause the video and think about before you go over the answer with me. We want to know, eventually, we want to get to the unfolding to the extent that this part over here will be exactly equal to 1, let's say, right? So we are making the following assumption, right? We're making the following assumption. Assume that over here, n, the input size, is exactly equal to 2 to the power of x for x larger than or equal to 0. So I think that's the assumption we are making. So we are saying that it will be perfect. It will be perfect for the input to be input size over here will be exactly some perfect exponents for the 2 over here, right? So that means eventually we can say that every time we're trying to divide it by 2, divided by 4, divided by 8, 16, 32, and etc. Eventually we can really get to 1 perfectly because of this assumption without the loss of generality. Okay, so here assume without is a very special term, very common term actually, whenever you do the mathematical proof. Without the loss of generality. Right? It's very important to see what our assumption is. always. Alrighty. And what I really want to have is this, t of 1. All right here. And then I should really get plus 1 all the way to plus 1. But now the question is, how many plus 1 should I have? Do I have over here? How many? Right? It's a very similar exercise as we did earlier over here, right? You can see that's what we did earlier. You can definitely use it as an inspiration point, right? All right, can you tell me how many there are? Once we know, we are done. All right, you can now pause the video and think about it. All right, assuming that you thought about it, in order to really get to see exactly how many plus 1 over here, we have to see the plus 1 in relation to the n over 2, n over 4, n over 8. That's what we have to do. Similar to what we did before, n minus 1, n minus 2, n minus 3. Similar, right? This is what I would suggest. We need to rewrite our input size slightly. That's what I would suggest. Okay. First of all, for n over 2 over here, let's rewrite it as n over 2 to the power of 1. Okay. And for n over 4 over here, let's rewrite it as n over 2 to the power of 2. Right? Similarly, for n over 8 over here, let's rewrite it as n over 2 to the power of 3. Finally, for this part over here, n over 16, right? N over 16 is really, I would like to have some curve actually. So let's say over here, this will be n over 2 to the power of 4. And now I wonder if you actually have found the pattern. The exponents over here, 1, 2, 3, and 4. When it is 1, let me just go back from the beginning. When it is actually equal to 1, we got only 1 plus 1. When we actually got exponent 2 over here, we got 2 plus 1s. When the exponent is actually 3, we got 1, 2, and 3 plus 1s. And when the exponent over here is actually 4, we got 1, 2, 3, and 4 plus 1s. That's exactly how you observe the pattern, right? Always, I think most likely you will have to rewrite the expression slightly for the input size, right? And how do we know how many plus 1s there are? So we have to turn this 1 over here into this particular shape, right? So that's a really critical part over here. So this is the 1 over here. Can we rewrite it in a way that is going to fit in this particular pattern? Like an n over 2 to the power of something, right? So we know that n is equal to n divided by n, first of all, right? And which will be equal to n divided by, we need to get into the form of 2 to the power of something, right? 2 to the power of this particular thing, right? Here's a question. 2 to the power of something is equal to n. What is that exponent? Well, for those of you who actually maybe study your, in the calculus course, I'm pretty sure you learned about some basic property for log of base 2, right? So this guy over here should be log n, right? So for any number, actually, let me just give you one example here. Let's see this concrete example. Let's say 2 to the power of, let's say log 8. What would that be? That's exactly equal to 2 to the power of log 8 would be 3, right? It's actually equal to the 8, right? You can see exactly corresponding to the 8 over here, right? I think that we did something very similar earlier when we did the dynamic array runtime analysis, the amortized analysis, right? But I'm just, it doesn't really hurt to really brush up quickly, right? Alrighty, so let's don't lose the big picture. 1 over here has been rewritten as n over 2 to the power of log n, right? You can see this log n over here is pretty much like the earlier exponents we have seen. which is 4, 3, 2, and 1. So now, how many plus 1s should we have? Well, depends on the exponent over here. So that should be log n. So that's the final answer. Log n. Right? We got log n terms. We got log n constant terms to be added up together. In that case, it's going to be big O of log n. Big O of log n. So that's really the final answer for the running time of the recursive algorithm of the binary search implemented in Java. Right? Let me recap very quickly. I know we are running out of time quite a bit, but I hope the time you spent with me doing this exercise from scratch is worth it. Right? Very quickly. Okay. So we are given this recursive algorithm over here. We need to, first of all, to formulate it, formulate its running time as the function t of n, right? So we're going to think about the base cases, typically 0 and 1, typically, right, for recursive algorithm. So in the case of 0, in the case of 1, you want to fill in what's really the corresponding running time. You don't really need to supply the exact number of primitive operations, just about if there's really big of 1, just put 1 over here. That'll be enough. And for the recursive case over here, in that case, you have to think about what's really the worst case. The worst case would be either we recur on this side or we recur on this side. Either side is okay because the size is going to be half. But the important thing is we don't really go to the either branch at the same time. So that's why this particular one is actually wrong. It's really important for you to see that, right? So once we have formulated the running time as a recurrence relation, we have to solve it. In order to solve it, we have to unfold it starting from over here at the top. And typically, you will have to do at least 2 to 3 unfoldings and then observe the pattern. You want to see exactly how many constant terms need to be added up before you can actually get to the base case over here. Basically about how many unfoldings you will have to do in order to get to the base case over here. Because for the base case, no more unfoldings need to be done. Once you get to the base cases over here, okay, let me just write it down. Once reaching here, no more unfoldings. That's why they're called base cases. Right? That's also a very important insight into analyzing the recurrence relation. Right? Once reaching here, no more unfoldings to be done. Right? That's why we have to see exactly once we get to t of 1. In that case, we have to make sure we rewrite the 1 over here in terms of something that we observe from the pattern over here. Because the way we rewrite it is n divided by 2 to the power of something. And the x can be 1, can be 2, can be 3, can be 4. And in this final case over here, it's going to be log n. So the number of terms over here will simply correspond to the exponent over here. All right. It's a very quick recap about what we have done. All right. So I think I need to stop over here for this week. I think we still got 3 more examples I really plan to cover at some eventually. I still got merge sort. I still got quick sort. I also got Tower of Hanoi. We'll see how we're going to cover in the later weeks. Stay tuned and then enjoy your study of the math and also analysis. And I'll see you next week.